Hope everyone's doing well. My name is Divya Mishra, and just to put it out there, it's great to see everyone here together, and it's been great hearing all the technical presentations so far. And I am very excited to kind of give this more conceptual and theoretical presentation that will kind of show a glimpse as to how I think we're heading towards the future in terms of our devices being connected and our networks, which includes both communication and computation. And thank you, Carol, for the lovely introduction. And thank you for RCA for giving me this opportunity of being here. So let's get right into it. So in today's agenda, we'll first be talking about some of the key technology use cases that will be used in the future that a lot of us have heard about, and how an artificial intelligence decentralized low latency edge ecosystem will help enable these use cases. Now that's a mouthful of words, but I assure you that by the end of this presentation, you'll have a better idea of what I'm trying to get at. And in order to understand such an ecosystem, we need to take a step back and understand the evolution of communications as well as computation over the past 2 decades to kind of get a sense of where we are going as a society. Then I'll be talking about 5G and AI in general, and what are the key things that these two technologies provide to us. Then I'll be going on to talking about how today's cities operate and how our devices are connected to the internet compared to how I see them being connected in the near future. And some of the key functions that we'll be talking about for this are federated learning, as well as a new novel way that we can initiate knowledge transfer across mobile edge cloud nodes, which I'll be getting into in detail. And the end result is a connected, intelligent edge ecosystem. So let's get right into it. These are some of the use cases that you've probably seen that are going to be very popular in the next 5 to 10 years or have already started to become popular. With transportation, we have the rise of self-driving, where in order to make a safe and reliable self-driving vehicle, we need to be able to analyze a lot of data in real time. With augmented reality and virtual reality, the same thing applies. We have a lot of video data and image data on which we need to perform computations on in order to present real-life seamless experiences to customers. With healthcare, we're seeing the rise of a lot of patient monitoring devices that a lot of people are wearing, and a lot of these devices are moving around cities and hospitals, and there's a lot of data being generated there. Similarly, in manufacturing, we have the rise of industrial IoT, where we have robots and additional production line monitoring systems, which will increase our efficiency. And with the rise of smart homes and our smart appliances, we're seeing a lot of data being generated that needs to be, a lot of analysis needs to be done on this data. So one thing that's common between all these use cases is that they all generate a ton of data, and we need to be able to do computation on this data very fast and in real time. And the two technologies that will enable this are artificial intelligence and 5G. And so the technology of the future that I'm kind of calling it is an artificial intelligence-based, data-driven, low-latency edge ecosystem. But in order to understand where this ecosystem is going and what exactly I'm talking about, it's important to go over where we've come from. And the two main pillars that will contribute to this ecosystem are a solid communication stack, as well as powerful computational abilities. So 5G, mobile edge compute, coupled with cloud computing and artificial intelligence, which we see today being used heavily, are going to be the key components for this ecosystem. So let's get right into the overview of communications. So in the 1980s, we saw the rise of 1G, where we saw the true version of a wirelessly connected world, and we started off with analog. Then with 2G, we transitioned into digital voice and saw the introduction of the SMS protocol. So a small amount of data was started to be transmitted. With 2.5G, we got email, web browsing, and basic camera phones. And not until we got 3G did we see some good amount of data speeds that could be achievable on our mobile devices. So this led to gaming being possible in real time and rudimentary video calling. With 4G, we saw even better video quality, much higher internet speeds, And now we can actually stream full HD games in real time. But with 5G, what we're focusing on now is how do we connect more and more devices in a particular area, and how do we connect more and more different types of devices? And in order to do this in a low latency manner. So that is where 5G's kind of main use case is. So as you can see, we have moved towards a more data-centric society, and the evolution of communications and communication protocols has shown that. And we are now using less and less voice. And as we're heading into the future with 6G and 7G, we're going to start to see the rise of ubiquitous internet, hopefully with satellite communications. But in order for us to even get to 6G and 7G, we have to figure out how do we locally scale 5G in the next 5 to 10 years to even take advantage of 6G and 7G. So now that I've kind of given an overview of communications, let's go into the history of computation. So in the 1980s, we started out with a very decentralized computational paradigm. We had large servers that were sitting in our basements, and there wasn't much connectivity between these computational nodes. With the introduction of mainframe computing, we saw people stacking a bunch of these servers together and connecting them. But not until grid computing became possible did we see large-scale server farms all around the world being connected through what we call the internet today. And this gave the rise to big data and Web 2.0, where now all of us use our mobile devices to access services, which are all on one centralized location called the cloud. This is where we store all of our data, where we perform heavy computations on our data, and we access this data from all of our devices. So we have moved to a centralized computing architecture. But in the last 5 years, we are seeing a trend back to our decentralized computing that we started at in the 1980s. With the introduction of artificial intelligence being possible through companies like NVIDIA and Qualcomm, who have been able to create GPUs and other forms of computation, we can now run a lot of computation on our mobile devices. And we don't have to rely on the cloud or a centralized place for all of this. And so with machine learning and blockchain encryption being two key enablers for the future, we have seen the rise of the term edge computing. And with edge computing, we're now moving the data and computation down closer to our devices from the cloud. So I'll be talking about what mobile edge cloud nodes are in a bit. But now that you kind of get a gist of where we're going and where we're coming from, it's important to understand where 5G fits into all of this. So the key benefits of 5G are that we are getting a much wider spectral bandwidth. So compared to legacy 1, 2, 3, and 4G technologies, now we have the 3 to 6 gigahertz band and the 24 to 100 gigahertz band. It can go up to 300 too. But the main point is for mid-band 5G and millimeter wave 5G, we're seeing speeds and data throughput of up to 10x more than LTE, which is going to give us a lot more data throughput. Next, we're seeing the introduction of massive MIMO, and with multi-user beamforming being the new way of trying to connect as many devices as possible in a dense region and different types of devices. And with higher cell density, we're seeing that more base stations, more cell towers will be deployed in a certain region. And the most important thing with 5G is now we're getting the option of adding private networks. So for cases where data privacy is a major concern, such as healthcare, where people don't want to send patient data all the way up to the cloud to some place in Virginia that's owned by Amazon, with these private networks, we're going to see the ability of use cases that we haven't seen before. So with legacy 4G LTE, we saw that we got good internet speeds, but with 5G now, with all these benefits, we're going to see this new pipeline of data called the mobile edge. And with the mobile edge, we're going to see the rise of mobile edge compute nodes, which I will be calling MECs for this presentation. And what an MEC is basically is with every base station that will be deployed on the 5G network, we're going to see a small amount of data storage capability as well as computation at the base stations themselves. But what is the driving technology for the edge? You may be wondering, like, why are we going towards pushing data and computation down from the cloud closer to our devices? And what exactly will the mobile edge look like going forward? So for the technology that's driving us towards the mobile edge, that is artificial intelligence. And there's two fields of artificial intelligence. One is called supervised learning. The other is called unsupervised learning. For this presentation, I'll be focusing mainly on supervised learning, and machine learning is the most common field for that. So you've probably heard a lot about neural networks. That is the main technology that's used for supervised learning. And the main concept is that through training a network, you basically feed it a bunch of data and you train it to say that for a certain piece of data, there's a correct answer. And you optimize these hyperparameters that are shown here in matrices to get to the correct answer for as many situations as possible. So a good example is like if you're trying to classify cats and dogs in an image, you would basically feed during training, you would feed the network a bunch of pictures of dogs and cats, and you would provide it the correct answer for each image. And in turn, through heavy computation, you'll be able to get optimized weight parameters for these matrices and these sum of weight equations. So the main important thing to get out of neural networks today is that there's two kind of pieces to machine learning. There's inference and training. Inference is when you've already trained the network and you have these weights optimized and found, and all you have to do is deploy this model on your devices and they'll run. And so inference is very cheap and very energy efficient, which is why on our mobile devices today, we are running neural networks. Some examples are like in order to detect your face for Zoom calls, when you blur the background, that's all happening through a neural network. When you're walking around the city, your location data, how it's being optimized, they're using neural networks. Another example is when we're communicating to our base stations with LTE, a lot of the spectral efficiency on what to use, what bands to use is being done with neural networks. So inference is something that we do really well today. And that's what is most commonly referred to when we say edge AI, the ability to run neural networks and run inference on our mobile phones and devices. But what the goal is for the future is we want to be training these networks as well, closer to our devices, not only in the cloud where there's a lot of computational resources. So in order to see what I'm talking about in a machine learning use case, I'll kind of give an example of what it looks like. So let's say we have our modern day city. We have our two base stations for LTE. We have cars, signal lights, planes, our phones. They're all connected to the LTE network. Right now with machine learning, what happens is we are running inference at all these devices, but in order to train the models, we send all this data through to the cloud all at once. So from our devices, we are sending data to our base stations. The base stations then route this data through data routers, through service gateways. Then this data goes through the IP packet network core for LTE. Then it goes through the carrier services network, and then it reaches the cloud. So you can already see that there's a lot of bottlenecks and errors that can happen here. So this whole system has a high data load, and also data privacy is a big concern, because if you're sending all this data to a centralized location, you don't want to be sending like very confidential data, for example, government related data or healthcare patient data. So in order to solve this problem, what the future will look like in this type of ecosystem, I like to kind of refer to how we solved the problem of bringing data to our CPUs as fast as possible. In the 90s and 2000s, we figured out a 3-tier caching system, which brought data down from our main memory much faster. And similar to this, what we're seeing now with mobile edge computing is with our mobile edge cloud nodes, we're able to bring quick access to data, but also quick access to computation at the same time. So as you can see, like with all these MECs, they're all deployed on these base stations, and they have their own mini data farm capabilities, as well as computational abilities. And they're all connected with each other and connected back to the cloud. So now in the machine learning use case, which will be driving a lot of the use cases that we want in the future, we're bringing the training down closer to our devices by training at these mobile edge cloud nodes. So data aggregation is not only more spread out, but we're also limiting data transfer by not making it go all the way to the cloud. So now that you kind of see where we're heading, and we're kind of heading to a paradigm where we need to be training our networks in real time. Not only do we want to train on the cloud and send it all back down through over-the-air updates, but we want to keep learning from our data and keep deploying updated models. So one good example I like to give is with self-driving cars right now. They're not self-driving, but how they work is they send all the data that's generated back to the cloud. Then engineers at these companies, they train the model for months. And then after a few months, an updated model is sent back to the cars. So there's not a lot of like real-time knowledge learning happening. And in the future, what I'm predicting is this will be something that's very big. And the way we're going to achieve real-time training of these models is through a combination of federated learning and a way of doing knowledge transfer of AI model information across MEC nodes. So with federated learning, what it is basically, it's still very conceptual and still very research focused. But what the basic is that you declare a neural network in the cloud, you send it down to your devices. So in this case, our phones. Then on our phones, you would train these models. And once you train these models, you upload these models back up to the global cloud. And the good thing is here is we're not actually transferring data. We're only transferring the hyperparameters that have learned certain trends from the data at these local devices. So we're preserving our customer information and data and also limiting data transfer. After this, we do model aggregation in the global cloud, and we can use averaging techniques to average these weights and hyperparameters. After this, we can do a global model update on all the devices. But you can already kind of see what the problem with this is today. The problem is that on our mobile devices, we don't have the computational abilities, and neither do we have enough energy to train these models on our phones. So where I see the industry heading is instead of our devices, this will be happening on the mobile edge cloud nodes. So each of these mobile edge cloud nodes will be training these models and sending back the information they've learned from their local data sets that are coming in real time. But this is great. However, what would be cool is if these mobile edge cloud nodes can be able to help each other out. So let's say that one mobile edge cloud node hasn't learned enough information or has a high error rate for a certain class in its neural network. Let's say for cats, it's not able to recognize cats very well. Well, it would want to learn from a neighboring MEC node how to fix itself, right? But how can we make that happen? How can we form these relationships? And in order to see how that can be done, I kind of wanted to give an overview of how model training kind of works today. Today with LTE, we send all of our data to a centralized cloud. We train on that cloud and send knowledge back down to our devices. Where we're heading right now is with mobile edge cloud nodes starting to be introduced in our cities. We'll see isolated learning happening at each of these nodes. But where we want to be is all these mobile edge cloud nodes talking to each other, transferring information about what they learn regionally across cities, and contributing to a global model that's sitting on the cloud that we know of well today. But how do we make this happen? How can we do all of this magic? So for this, we have four main components. First of all, we'll need a centralized way to keep track of all the neural network information of all the neural networks at each mobile edge cloud node. And secondly, we need to figure out a way to initiate a model transfer, knowledge transfer request from one node to another. And third, we need to find a heuristic that will find similar neighboring MEC nodes to get the best knowledge as possible. And then fourth, we need to also implement a way to combine knowledge into the machine learning models together at the end. So let's get into the first component. Let's say we have our network of mobile edge cloud nodes. Periodically, they will need to be sending updates on how their neural networks are performing, whether that be through periodic updates or through threshold-based updates. And what will happen is here I've shown there's these different MECs. For each MEC, we store model information such as estimates of class priors. So this is basically just a probability distribution of what data sets are coming in to that node to train the model. And here we're storing the per class model error rates after the model is trained at each MEC node. We also stored the overall model error rates and the training and inference numbers that are at each MEC node. So this is kind of a centralized system that will be stored on the cloud to kind of store information about how neural networks are operating across different nodes. A good example is like in Atlanta, you could have this node in Buckhead, this node in Suwannee, and each node will have different input data that trains its network, right? And so this is a good way of centralizing all that data. So now that we have a good way of storing what's going on at each node, we want to figure out a way to initiate knowledge transfer. So let's say that we have a bunch of data that's training a model at an MEC node. We will establish some thresholds for each model class or the overall model. So let's say we're training on dogs and cats, classifying them. We can establish a threshold for cats saying that if the accuracy of the model is below 70%, we need to initiate a knowledge transfer request. So this is a good way of kind of getting that request going, but how do we know which MEC node to transfer knowledge from? Which MEC node will help? For that, we can use a similarity detector. So if you recall, I showed you some of the data that can be stored on the cloud. By comparing the probability distributions between the same model running across different MECs, you can figure out which MECs are similar in nature. Once you have that, we can use like chi-squared statistics or the Jensen-Shannon divergence, which give us a number between 0 and 1 to show how similar the MECs are to each other. Once we have a list of those, we can prune the list to only include neighbors with low model error rates. So let's say that our MEC in Suwannee, Georgia is not able to classify cats. Well, maybe the one in Buckhead has a very similar data distribution that was used to train it. And its cat classification error rate is like, accuracy rate is like 95%. So we want to transfer that knowledge. So now that we know that, we can just filter based on which classes we want and the highest accuracies. So once we have what MECs will use, now we have to figure out how to combine that knowledge into the current MEC node that needs to be updated. And so for this, there's techniques like with the one versus rest approach or the bagging approach. I'm not going to get into super details about how these algorithms work, but all you need to know is that the information for, let's say, cat classification will basically be combined with the model that needs to be updated, specifically for the area of the network that classifies cats. So this is kind of, all of this basically enables a collaborative learning environment at the edge, where we have all these mobile edge cloud nodes collaborating with each other, learning information regionally, and updating a global model that encompasses all this information. So the end conclusion is that we are limiting data transfer from our end devices, and we are also conserving computation because we're moving it down closer to our devices. We're also preserving customer data because we're not sending all the data up to the cloud. Rather, we're sending it up to these MEC nodes, and these can be private networks. So that problem gets eliminated. Third, the advantage is that we're learning regional knowledge. So an example where this could be useful is if we have a language translator, let's say, a person who comes from India may have an Indian accent, and they come to the United States and they use a translator, and the voice assistant is not able to pick up what they're saying with the Indian accent. So a use case of this could be the MEC nodes in India will be training there, and there's MEC nodes in the US, and we're able to combine all this knowledge into a global model. So now a translator or a voice assistant in the US can now recognize an Indian accent. That's kind of a very rudimentary example. But now all of this basically enables a lot of these use cases of the future that we talked about. So with that, here are the sources. And I would just like to, again, thank everyone here, Ellie Van Winkle and Rip Van Winkle, and Carol. Without these three individuals, I would not be where I am today. And I appreciate for all of you being here and listening to me. Thank you.
Questions for the speaker?
My first slide. Can I go back?
Your agenda.
Oh, okay.
We got time, right?
This slide or the next
The
one?
next one.
This one?
So was this on purpose, the order?
Yeah.
So can you go back to the, show the list?
Yeah.
Because you're jumping from numbers. Do you know?
Oh, I skipped a 6. I just realized.
Okay.
Oh, you're talking about the 6,
yes,
right?
yes.
Okay,
It's
okay.
missing the 6.
Okay, yeah, that's a typo.
So there's no information missing.
No, there's no information missing. Yeah, yeah.
Sorry, I just like to catch that.
Good eye. Yeah. Yes.
Well, I could probably talk to you about the whole thing for 3 days straight, but being an ex-Verizon guy and working in the autonomous vehicle program for quite some time and still to today. Oh, okay, I'm sorry. So being in this field and working in autonomous vehicles from Verizon and now in my current company, so the gold standard today is to spread out our compute power with some of our compute at the edge and some at the rack, as we're now calling it, regional edge compute. And then we have our hyperscalers, right, that will do the big brain activity. And so the bird, deer, something, coming in front of your car, that precognition of AI, or already knowing from a sensor package in the neural network that there potentially is a deer halfway, let's say a quarter mile up the road, that tells your vehicle, hey, by the way, there's a deer. Now, that only comes to the neural network, and the compute power needed to do all that computation is dependent upon latency.
Correct.
right? So the closer I am to the deer coming out in that precognition is where my compute latency lies. So is it at the edge? Is it in the rack?
Are you referring to the,
I'm referring to the gold standard of a 55-mile-an-hour
okay, so
drive at
just like
100
during
mile-
inference,
at a
right?
100-mile skid test, crash test.
Yeah, so you're referring to inference, if I'm not mistaken, and
Inference,
like
correct,
where the car sees it happening and it needs to make a decision immediately, right?
correct. The
For
40 milliseconds.
correct, yeah, we already have that technology in our cars today. Teslas, they use inference very heavily, but what I was talking about more was how do we update this knowledge that's being inferred upon? So the inference that's happening, that's on a trained model that was trained in the cloud for a long time. A lot of engineers worked on it, and they sent that neural network down through an over-the-air update to the car. And so the car itself is not learning new information. That process is not real time. So that's what I was kind of getting at in this talk, is how do we make a system, self-driving is one example, where we can continuously, let's say that in the same deer example, like if a car sees the deer and let's say it hits the deer, let's say the neural network was not trained in the right way to address that situation. Tesla and like some other companies, they've already figured out ways to create ground truth data based on occurrences that happen. So what the goal is you want to make other cars there, you want to update their knowledge. If
Well,
this
and
happens,
that's the V2V, right? So
yeah,
that's the
vehicle to
conundrum
vehicle
we,
is,
yeah.
yeah, vehicle to vehicle is a separate actually conversation. That's more concerning one car talking directly to another car
Or
and its
indirectly
surrounding.
through the Mac.
Yeah, okay, yeah. So if you're,
So the first car passed the deer, saw the deer, the deer did not collide with the car, but the deer is now standing still, telling the vehicle behind, because that car now told the other car, hang on, he's there, just slow down. So
yeah,
there's already a precognition for that to happen
yeah,
with the V2V, but it can still be V2M through the Mac. Just
yeah,
vehicle to vehicle.
yeah,
And that's the misnomer. V2V does not mean car to car. It means car to cloud to car.
that's called cellular to vehicle communication, CV2X. Yeah, and then
yeah, it's just everybody's tossing around new analogous names as they go along.
yeah.
But yeah.
But the difference that I was trying to highlight is the thing you're talking about, vehicle to vehicle, that doesn't involve neural networks usually. So how that works is if there's a car and it sees a pedestrian in front of it, but a car behind it can't see it through its radar systems or something like that, it can tell that car behind it that, oh, there's a pedestrian at this location relative to you. So that doesn't involve any like knowledge per se. But the situation that I was talking about was, let's say that the car hits the deer. And now there's a data point in the system where the car has hit the deer, but the ground truth data said, oh, the car should have stopped at this speed or whatever the ground truth data is. Then you have to go back, and if you want to update all the other cars in that area or even around the US, how are you going to do that in real time?
Well, it's
right?
kind of in automatic ways, right? So let's say there's already a deer that crosses there every night at 6 o'clock, or a bunch of deer, just because that's their migration path. So now if there's sensor packages in the road, or there's sensor packages anywhere, or a car already knows this, and there's accumulative data and it goes to the big brain can tell everybody, hey, there's always deer crossing through this area. So I'm going to slow you down to 25 at around 6 p.m. just because I already know that this event could happen.
Yeah, so that's like where the MECs come in handy,
That's
right?
where the MECs come in handy. And to your point about the computation power in the vehicle, and that is where the automotive companies want to remove it from the vehicle and put it into the cloud, because that's an additional cost in the vehicle that you don't want to incur as a consumer, because that's a lot of compute power and a lot of storage power that needs to be done in the car, and they'd rather do it in an edge in a shared fashion.
Yeah,
which
so
I know
the
Qualcomm shares that vision as well.
yeah, the compute that you're talking about is not related to inference, right? That's related to training. And yeah, that is anyways right now not being done at the car itself. So yeah. Any other questions? He had a question.
Last question.
So federated learning is great for situations where you have not a lot of training data on the rare but disastrous occurrences. So in the case of self-driving cars, it's difficult to generate your own training data for all of the various ways things can go wrong on a road. And so you try to gather that data from as many sources as possible by having all of your cars give you data. The challenge, though, then, is that you have less control over your training data set. And it seems like it opens up the possibility of adversarial training, where a bad actor inserts particularly calculated training data into your network to be used to train future models that cause the trained model to behave poorly,
Malfunction.
or malfunction, or to allow them, through a security system that they shouldn't be allowed through. To what degree is it possible to sanitize that incoming training data and verify that it's actually good data?
That's a really great question to which I don't have a very specific answer. That's actually a very big research field, is how do we encrypt all these hyperparameters that are being learned, right? And especially with very confidential data, right? Like if you have a heart patient's readings, you don't want anyone to figure that out with the hyperparameters, backtrack it to the actual data that was used to generate those parameters, right? So there's a whole industry of like figuring out how to encrypt that stuff properly. But the main benefit is that right now we're transferring all the data we can. That's like each self-driving car is projected to generate like 1.5 terabytes per hour. So if you do the math, how many cars are on the road, how much data we'll need to send to the cloud, like it's just not feasible. So this is just a solution for that. But very good question. I don't have a very like direct answer on how to encrypt the training data, but it's being worked on for sure.
Okay, thank you very much. Thank our speaker once again.